Okay, so thanks. I'll be talking about some joint work with Sasha Kuznetsov, so on derived categories of cyclic covers. At least two of you a few weeks ago heard Sasha talk about something called Gushel Mukai varieties, which is a different project we had been working on. And so I decided to talk about something different, but as you'll see, it is related to what Sasha was saying. So okay, so first let me say that we'll work over a field K, which I'll assume is algebraically closed and of characteristic 0. Although for most of the things I say, it's okay if the characteristic is not 0, as long as the characteristic is prime to the degree of the cyclic covers we consider. But anyway, let's stick with this assumption. So I'll be talking about derived categories, and for a variety x, I'll just write d of x. So this is the derived category, and really what I mean is the bounded derived category of coherent sheaves on x. So this is the basic object that we'll be studying. And one of the main ways you can get your hands on the derived category is via the structure of its semi-orthogonal decompositions. So let me just briefly remind you of the definition of that. So the definition makes sense for any triangulated category, and this is an example of one. And we'll work with triangulated categories that are linear over the space field throughout the talk. So let's say that T is a triangulated category. Then, by definition, a semi-orthogonal decomposition of T. So I'll use the following notation for this. I'll write T equals brackets A1 through AN. So what is this thing? It's a sequence of categories AI. And these categories are required to be full triangulated subcategories of T. And we impose two conditions. Okay, so the first condition is the semi-orthogonal part of the definition. So it says that HOMs from AI to AJ are equal to 0. And this is for I greater than j. So this is just shorthand for, I'm saying that for every object of AI and for every object of AJ, there are no HOMs. And this is when I is bigger than j. So that's why it's called semi-orthogonal, because in general there may be HOMs in this direction, but what I'm saying is there are no HOMs from the right to the left. So this is the first condition. And the second condition is the decomposition part. And it says that for every object in your category, say F, there should exist a sequence of morphisms which starts at 0 and it ends at your object F. And I require the following condition, which is that the cone of Fi mapping to Fi minus 1, this should lie in the category A sub I. So the way you should, roughly speaking, it says that for every object, you have a filtration whose successive quotients lie in these categories AI. So that's the decomposition part. So maybe I can just give you a few examples of this. So somehow the first mandatory example, and it was really maybe the first interesting example of this kind of thing, is the derived category of Pn. So that has a decomposition which looks like this. So it has n plus 1 pieces. So let me clarify a little bit what I mean here. So strictly speaking, I should give you subcategories of the derived category. And to say what I mean here, if you look at any one of these objects, let's say E, say E is OI, then this object is what's called exceptional. So by definition, this means that if you look at the self X of E with itself, then this is just a copy of the base field K concentrated in degree 0. And whenever you have such an exceptional object, you can look at the triangulated subcategory, in this case the subcategory of the derived category of Pn, that this thing generates. And the fact that this object is exceptional implies that this thing is equivalent to the derived category of a point. So the derived category of vector spaces over K. And the equivalence is just by taking a complex and sending it to V tensored with E. Okay? So what I mean when I write this is really that this is shorthand for the category generated by O of 1. Okay. And I'll use that notation throughout the talk whenever I have an exceptional object. So this is the first example. And yeah, I guess I should say that this is due to, it goes back to Bailenson. Okay, so let me give you one more example of a semi-orthogonal decomposition. So this one will be relevant for an example that I do later. And it's the Grassmannian of two-dimensional subspaces of a five-dimensional space. So let me call, I need some notation to tell you the decomposition. So let me call U the rank 2 tautological bundle on the Grassmannian, and O of 1 will be the ample generator of the Picard group, which you can also write as the determinant of U dual. Okay, and so in this case, this Grassmannian, it has a decomposition. Its derived category is a decomposition that looks like this. So there's one copy of O, then U dual. Then you twist these things by 1, and in total there are 10 objects that appear. Okay, and so yeah, by the way, all of these objects are exceptional in the sense that I just defined. Okay, and so this is a decomposition for this particular Grassmannian, and this goes back to Kapranov. Now, I mean, there are many examples of semi-orthogonal decompositions. There are ones for every Grassmannian, but I just want to focus. Later, I'll use these in some examples. So I wanted to write these two. And so both of these examples have the same form. So what I want to point out is that in both cases, we have a variety Y. So a variety Y. And I have a line bundle O of 1 in the Picard group of Y. And I have a decomposition that looks like this. So d of Y equals B twisted by 1. So here, B is just some subcategory of the derived category of Y, some triangulated subcategory. And this is my notation for, so the obvious thing, it's B tensored with O of 1. So it's the image of B under the auto-equivalence given by tensoring with O of 1. So in the first case, you could take B to be the category generated by O. And in the second case, you could take B to be the category generated by these two objects. Okay, so both of these examples are of this form. And actually, there are many other examples of varieties with interesting decompositions that look like this. So for instance, you can look at a Grassmannian GKN, where K and N are coprime, and that has a decomposition like this. You can also look at other types of Grassmannians, like some orthogonal Grassmannians, some symplectic Grassmannians also have this kind of decomposition, and also weighted projective spaces, as long as you think of them as stacks, have such a decomposition. So there's a good supply of these kind of things, and in general, this is called a rectangular Lefschetz decomposition of the derived category. Okay, so this kind of thing goes back to Kuznetsov's work on homological projective duality. And let me mention that here the word rectangular refers to the fact that it's the same category B appearing on all of these pieces. And Lefschetz decomposition comes from the fact that this kind of decomposition behaves well with respect to taking hyperplane sections. So I'll explain a more general instance of this fact in just a minute. So first I want to say that for the rest of the talk, we'll work in the following setup. So I'll assume that I have a variety with this kind of decomposition. And like I said, there are lots of examples of this kind of thing. I'll take Z to be a divisor in O of ND. So here N and D are just some positive integers. And let's assume for this talk actually that this is a smooth divisor. And while we're at it, let's also assume that Y is smooth and projective. So in fact, neither of these conditions are necessary, mostly for psychological reasons. Let's just assume this. And let me set X to be the degree N cyclic cover of Y, which is ramified in this divisor Z. And I'll call F this cyclic cover map, and I'll call I the inclusion of Z into Y. Okay, so this is the setup that we'll be working in. And the first thing I want to explain is how this decomposition induces decompositions of X and Z. Okay? And I'll just write, in this talk, all of the functors are derived. So like I pull back denotes the derived functor from d of Y to d of Z. And the statement is that this is fully faithful on that subcategory B. So on B, provided n times d is sufficiently small. So you need n times d to be less than n. And the second part, well, so there are two parts to part one and then two parts to part two. So the second thing is that we can look at the analogous thing going from d of y to d of x, so the pullback by f. And again, the same thing is true. And here the condition that you need is that n minus 1 times d is less than m. So I'll explain these conditions in a second. And the second part of the lemma says that we have semi-orthogonal decompositions. So first, for d of z, you have a decomposition that looks as follows. So you have something I call a of z, and then a bunch of copies of this category B. So here, I'm defining B of z to be I pullback of B. And so this embeds, this category B embeds into z of z as long as this condition is true. And this decomposition that I'm writing is for nd less than or equal to m. So notice that I allow nd to be equal to m here. And in that case, there are just no copies of bz, and I'm defining az to be everything. OK. And what is this category A of z? So A of z is defined to be the thing such that we have a semi-orthogonal decomposition. So in other words, it's the full subcategory of f such that Hams from G into F are 0 for every G which is inside of the category generated by these B. So I mean, that's exactly defining A of z so that you have a semi-orthogonal decomposition. And similarly, there's a decomposition for d of x that looks like this. And this holds for n minus 1 times d less than or equal to m. OK, so let me briefly explain why this is true, just so you have a feeling for the lemma. I'll say how you prove part one. So let's prove part one of the lemma. So what do we have to do? I mean, let's take f and g, which are in this category B, and let's just compute Hams from I pullback of f into I pullback of g. OK, and so what is this? That's the same as Hams from f into I push forward of I pullback of g. And I can also write this here as g tensored with O of z. Yeah? OK, so now there's something sort of obvious that you can do. You can look at this exact sequence on Y. So just the resolution of the structure sheaf here. And you can tensor this with G, and then you can Hom from F into it. And if you do that, you get a long exact sequence that looks like this. So you'll have Homs from F into G minus ND, Homs from F into G, Homs from F into G, tensored O of Z. And so this is a long exact sequence, and the next term is this. Okay, so you get this kind of long exact sequence, but now notice the following thing. So this Hom group, well, if you want, you could rewrite it as F twisted by ND mapping into G. And this thing vanishes, yeah, because we assumed ND is less than M, and by assumption we have a semi-orthogonal decomposition like this. So there are no Homs from the right to the left by the definition of a semi-orthogonal decomposition. So this thing is 0. And for the same reason, this is 0. So these are all zeros, so this is an isomorphism, which is exactly what we wanted to show. So Homs from F into G are isomorphic to this. Okay, so that thing is fully faithful. And maybe just to mention why you get n minus 1d here, it's just because in the case of F pullback, you'll end up considering F push forward of F pullback of G, and you can write that as the direct sum from t going to 0 to n minus 1 of G twisted by minus td. Yeah, and so this is where n minus 1 times d is coming from. Okay, so that's how you prove part 1, and part 2 is you can do by a similar technique. You just need to check that these components are semi-orthogonal to each other. So that's how you prove this lemma, and the way that you should think about it is that if you take a divisor in Y or a cyclic cover, assuming the degree is sufficiently small, then you get an induced semi-orthogonal decomposition with a bunch of components coming from the ambient variety, and that you get something else left over, which is, you should think of it as the interesting piece, the part that doesn't come from Y. So these are sort of the interesting pieces of the derived categories. And the goal of the talk is to explain the precise relationship between these two categories. And so let me add to our sort of standing assumptions that n times d is less than or equal to m, so that both of those categories are really defined. Okay? And it can be, I mean, it can go up to Calabi-Yau.
But then you're saying it's vague. Yeah.
No, so this one will be non-trivial still. I mean, in the case where m is equal to nd, this will be the whole d of z, but you actually do get something interesting. Yeah. So maybe I'll say an example of that later. Okay, so from now on, we'll assume this. And the goal is to say a relation between these two categories. So what can you do? I mean, one thing that we have naturally given to us is acting on x. We have the nth roots, I'll call mu n the nth roots of unity, acting on x by automorphisms over y. And so that action of mu n induces an action of mu n on d of x. And this action of mu n, it preserves all the components in this decomposition. The reason is just because these bx are pulled back from the base y. So certainly acting by the automorphisms of x over y takes this category to itself. And so by the definition of ax, mu n also preserves ax. So what we get out of this is we have this action on ax of mu n. So before I state the theorem, I just want to remind you a little bit about group actions on categories. So let's say that I just have some category C, and I have an action on it by a finite group G. So I'll be considering right actions. And so what does this mean? I mean, to have a group action on a category means that for every element of the group, I should give you an autoequivalence of C. And for every pair of elements, G and H and G, I should give you an isomorphism of functors. So G times H pullback to H pullback composed with G pullback. So this should be an isomorphism. And this should satisfy a natural associativity condition, which I won't write. So this is what it means to have an action of a group on a category. And you get one, for instance, from automorphisms of X that gives you an action on D of X. And whenever you're in this situation, you can consider the equivariant category. Equivariant category of C with respect to this action. So my notation for this will be C upper G. And what is this thing? So an object of this equivariant category is just a pair, F comma phi. So here, F is an object of the category C, and phi is a linearization of F with respect to this group action. So what it means is that for every G in the group, I should give you an isomorphism between F and the pullback of G acting on F. And again, there's some natural compatibility condition, which I won't write down. So this is what the equivariant category is. And one remark I want to make is that in this talk, we'll be considering the case where this category C is triangulated and G acts by exact autoequivalences on this triangulated category. So in that setting in general, this equivariant category is not necessarily triangulated in the natural way. However, in all of the cases we'll be considering, that is true. So for instance, for this kind of action. So I'll sort of just suppress this point from now on, but everything is OK there. These categories are really triangulated. And I mean, maybe just as a sort of the most simple example of that, say that G was acting on a variety X, then you get an action of G on the derived category. And this equivariant category is exactly what you think it is. It's the derived category of equivariant coherent sheaves on X. Okay, and so in particular, it's triangulated. So this is sort of the most basic example. Okay, so but now that that's out of the way, I can tell you what the theorem says. So here's the theorem. It says that there are fully faithful functors, which I'll call phi sub k. And these functors go from the category AZ into this equivariant category, which I just told you what this thing means. And we have these functors from k, so there are n minus 1 of them, from k equals 0 to n minus 2. And they satisfy the following thing, which is that if you look at the images of AZ under these functors, they give you a decomposition of this equivariant category. Okay, and maybe I can point out an especially nice case is when n is equal to 2. So when n is equal to 2, what does this say? It says that this equivariant category is just equivalent to the category A sub z. The equivalence is given by this functor phi naught. Okay, and moreover in this case, you can show the following thing. So there's an action here of z mod 2 on AZ, and you should think of z mod 2 as being the characters of mu 2. So the reason is that this group of characters acts naturally on this equivariant category. I mean, I'm just saying that in that description of the objects of this category, you can twist the linearization by plus or minus 1. So that's the action of the characters on this category, and so you get an induced action here via this equivalence. And the statement is that AX is actually, AX itself, not the equivariant category, is equivalent to AZ Z mod 2. So with respect to the action I just described. Okay, so this is the theorem. And before I say something about the proof of it, I want to just do a few examples to show you what it says in some cases where it might be more familiar to you. So, okay. So examples. So the first example I'll consider is related to 2 up there, to this Grassmannian G25. So let's look at the following case. So I'll take Y to be the following 5-dimensional variety. So I take this Grassmannian G25, and I take a hyperplane section. So a hyperplane section inside of the Plücker space. So this is the Plücker embedding. And the derived category of this Y has a decomposition that looks like this. So there are 4 pieces here. So let me say something about this. So you see the example up there gives a decomposition of the derived category of this Grassmannian with 5 copies of this category B. So by the lemma I showed you, you do at least get 4 copies of B inside of Y, just because it's a hyperplane section of this Grassmannian. And what I'm saying here is that that additional piece that you get actually vanishes in this case. So that's not obvious, but it's true. So I'm just telling you the derived category of Y, this hyperplane section, actually everything in it comes from the ambient variety G25. So we have a decomposition like this. So this will be our variety Y in the setup over there. For Z, I'll take a quadratic section of Y. And if you look at the derived category of this Z and you apply this lemma, then you get a decomposition that looks like this. And so X will be the double cover of Y, which is branched in this Z. So the derived category of X in this case looks like this. And what the theorem tells us in this case is that we have equivalences like this. Well, I guess it's exactly what I wrote right above this. So let me make some remarks about this, which maybe illuminate the example a little bit. So first of all, maybe I'll keep this lemma. So the first remark is that, and this is why we originally looked at this example, is that both of these varieties, X and Z, are examples, so they're Fano varieties, and they're examples of these things called Gushel Mukai varieties. So by definition, a Gushel Mukai variety, a Fano Gushel Mukai variety, is a Fano variety with Picard number 1, degree 10, so I mean the degree with respect to an ample generator of the Picard group, and co-index 3. So in this case, it just means that k of x is negative 3h and k of z is negative 2h. Okay, so both of these x and z, they're Fano varieties with the same numerical invariance, but they're in different dimensions. And this shows that there's some kind of coincidence between their derived categories. And so what I want to say now is that this kind of relationship is actually exactly analogous to the relationship between a K3 surface and an Enrique surface, in the case where the K3 has an associated Enriques. So let me call T an Enriques surface. Let me call S its K3 double cover. Then the following thing is true. So we can look at the derived category of this Enrique surface, d of t, and we have acting on it the group mu2. So I guess normally I would just write z mod 2, but I'm trying to stick with the notation I set up. So the action of mu2 here, so this acts by tensoring with the canonical bundle of t. So this is an Enrique surface, so that's some two-torsion line bundle. And so we get an action of mu2 on this category. And that equivariant category that you get is actually just equivalent to the derived category of the K3S. I mean, that's precisely because S is the twofold cover corresponding to this two-torsion line bundle. So if you unwind what this linearization means, you see that it's exactly the same as giving a coherent sheaf on S. Okay, so you have an equivalence like this is the first remark. And also, you have an equivalence between the derived category of T and this equivariant category, where here z mod 2 acts by the involution of this cover. Okay? I mean, that's just a standard fact, that when I take the quotient, I get equivariant sheaves, which is exactly the derived category of T. So we have these two equivalences, which, okay, that looks very similar to what I wrote over here, but the analogy is even a bit stronger. So if you look at the Serre functors of these two varieties, then the Serre functor of d of t, well, that's given by tensoring with omega t and shifting by 2. Okay? And the Serre functor of d of s, this K3 surface, is just given by the shift by 2. So maybe, by the way, just to remind you what I mean by Serre functor, it's just a functor that implements Serre duality. So it means that Hams from f to g are isomorphic to Hams from g into s of f dual. Okay, so this is what it means to have a Serre functor in general on a triangulated category. And Serre duality more or less says that for a smooth projective variety, this is what the Serre functor looks like. So we have the Serre functors, and they look like this. And in the case of these categories, it turns out that the Serre functor of a of x is given by tau twisted by 2, shifted by 2, where here tau generates that mu2 action. Okay, so tau is exactly the autoequivalence of ax that you get by this involution of x over y. And it also turns out that the Serre functor of az is given by shift by 2. So at the level of Serre functors and at the level of this equivariant categories, it really looks like we're somehow exactly in the same kind of case as you have with an Enrique's and its associated K3 surface. So that might lead you to ask, I mean, are we ever actually in that situation, right? Is it ever the case that AX is the derived category of an Enrique's, and is it ever the case that AZ is the derived category of a K3 surface? So that's the third remark, and I'll write it as a theorem. So I won't really discuss much the proof of this here, but I think it helps understand what's sort of behind this example. So the theorem says the following. It says that this category AX, that's never equivalent to the derived category of a smooth projective variety. It's also true that AZ is not equivalent to the category of a smooth projective variety if Z is very general. So for Z very general in moduli. However, we showed that there is a codimension 1 locus inside the moduli space of Z, such that AZ is equivalent to the derived category of a K3, so the K3 depends on Z. And here this is a degree 10 K3 surface, and it happens for Z in some, I mean, we construct explicitly this locus for Z in a codimension 1 locus in the moduli space. So I think I won't say so much about the proof of this theorem, but I just wanted to tell you. Maybe I'll say that this you can prove using Hochschild homology. This follows from the fact that for a general Z, the K theory is too small, and this is more complicated, and you really have to do some work.
Can you specify the very general modern subset?
Very general here. So at least you can say that there are certain Hodge theoretic divisors where these Z acquire an extra cycle, and away from those, it can't happen. Yeah. So, okay, so I think this is all I wanted to say about these Gushel Mukai varieties. And now let me do an example where this n isn't 2, where n is 3. So, yeah, I guess I'll erase this now. So the next example that I'll do is cubic fourfolds. Okay, so here's example 2. So in this case, I'm going to take y to just be P4. And the derived category of this y, I just erased it, but it has this standard decomposition with five exceptional bundles. I'm going to take for z a cubic threefold. This is a cubic threefold. And if you look at what that lemma gives you that I just erased, I mean, you can just believe me, you get a decomposition that looks like this. And I'll take x to be a cyclic cubic fourfold. So it's a triple cover of this P4 branched in this Z. So this is my x. So this x is a cubic fourfold. And concretely, the cubic fourfold lies inside of P5, and it's defined by some equation, let's say like this, where here Z is defined by that equation G. Okay? And the derived category of this x, so let me write down for you how it looks. You get AX, and then you get three exceptional bundles. Okay? And what does the theorem tell us in this case? So the theorem says that this category, AX mu3, it has a decomposition into two pieces consisting of this category AZ. Okay, so let me make some remarks about this, sort of similar to the way I did up there. So the first thing I want to say is that, well, in general, whenever I have a triangulated category, Serre functor is shift by 2, I'll call this a K3 category. So it has a Serre functor, which looks like the same one of a K3 surface. So this AX is actually a famous example of a K3 category. And it's the one that Kuznetsov studied when he studied rationality of cubic fourfolds. So this is a K3 category. And it turns out that this category AZ is not geometric. Where here, by not geometric, I mean exactly this thing, that it's not the derived category of any smooth projective variety. So what the theorem says in this case is that you get a decomposition like this, and there's sort of not much more you can say without making additional assumptions. I have this K3 category that splits up into the derived category of two non-geometric things coming from a cubic threefold. So let's make an additional assumption which makes the example a bit nicer. So what I'm going to assume is that this Z, I'll assume that Z itself is a cyclic cubic threefold. Okay, so it's a cyclic cover of P3 branched in some cubic surface. I'll call it W. So X is, so to speak, a double cyclic cubic fourfold. And what this means is that this equation, I'm assuming that it looks like this in suitable coordinates. Yeah? So this is the equation defining Z, and this now defines W. Okay? And if you look at the derived category of W in this case, the corresponding decomposition has this form. So A of W, O. Okay, so this is the decomposition the dilemma gives you. And the remark I want to make is that this category here, it's actually generated by 8 exceptional objects. So the way that you can see this is that, so this W is a cubic surface, so it's the blow-up of the plane in 6 points. You can see from that that it has a decomposition with 9 exceptional objects, and this is one of them. So this thing is really generated, this thing has a decomposition with 8 exceptional objects. Okay, and so what does the theorem say? It says that the equivariant category here, so to write it coarsely what the theorem says, it says this has a decomposition with 16 exceptional objects. More precisely, it has a decomposition made from 2 copies of this thing. So you get a decomposition like this of Z, the equivariant category of AZ. And so now, the thing I want to remark is that, so I'm assuming this now, and on this original variety X, we now have an action of mu3 times mu3. So the first copy of mu3 here is just acting by scaling on this coordinate x5, and the second mu3 acts by scaling on this coordinate x4. Yeah, so I have an action of mu3 times mu3 on x, and this thing induces an action on AX. And I can consider its equivariant category. And so maybe I won't say all the details, but if you combine this and this, then these two things together, this decomposition plus that one, you can use to see that this has a decomposition with 32 exceptional objects. So this, I think, is a bit more interesting for 2 reasons. So the first is that if you just look at this category AX, it's a K3 category. And these kinds of categories don't have any semi-orthogonal decompositions. So it says that if I pass this equivariant category, I get something very simple in the sense that it's just made up of a bunch of copies of the derived category of a point. And another thing is the following. In this situation, so I'm assuming everywhere here that X is one of these double cyclic cubic fourfolds, then X is itself actually rational. And this category AX is equivalent to the derived category of a K3 surface, which depends on X. So the way that, for instance, you can see that this is rational is that it contains 2 disjoint planes. You can take, for instance, every line on W gives rise to 3 2-planes on X. And if you take 2 disjoint lines on W, you can see that you get 2 disjoint planes on this fourfold X. So that means that X is rational. And you can also check that, in this case, AX is equivalent to the derived category of a K3 surface. So what it means is that ultimately this example gives you an interesting, I mean, it's a very strange action of mu3 times mu3 on the derived category of a K3 surface with this, in some sense, very simple equivariant category. OK, so that's the second example that I wanted to do. And now I think I'll say something about the proof of the theorem. So maybe just about the ingredients of the proof. So I think actually maybe it's better if, well, it might be better if I do it on this board. OK. So here maybe some ingredients in the proof of the theorem. So the basic idea is that we'll look at the derived category of X, and I'll look at this equivariant category. And what we'll do is we'll write down 2 different semi-orthogonal decompositions for this category, and then compare them. And sort of that's the basic outline of the proof, but let me tell you some more details. So here's the first ingredient. So if you remember from the lemma in the beginning, if you look at the derived category of X, it has a decomposition that looks like this. So this was the decomposition I wrote down in that lemma earlier on. And on this category, I have an action of mu n, which preserves all of these components. And it actually follows in this case that if you pass to the equivariant category, you get a decomposition whose components are the equivariant categories of the components. So this isn't completely obvious. It follows by a theorem of Elegant that this works, that you actually get a decomposition of this whole equivariant category into these pieces. Now, the second thing to notice here is that let's focus on one of these bx's, say bxt. And let's look at the equivariant category of this thing. So this actually, I mean, how does mu n act on this bx of t? Well, the action is trivial, actually, because everything here is pulled back from y. So mu n acts trivially on this category. And as you might expect, that implies that there's a decomposition that looks like this. So it's just indexed by the representations of mu n. So here I fixed a primitive character of mu n. Yeah, and in fact, I mean, this isn't just a semi-orthogonal decomposition. It's just completely orthogonal. There are no Hams in any direction. So we have a decomposition of all of these components into a bunch of copies of this category B. And what it means is that, so to write it kind of coarsely, this equivariant category has a decomposition into the thing we're interested in, this guy here, and then it has some number of copies of B. So what's the number? So I have n times m minus n minus 1 times d b's. Okay? So if you just plug this into all of those copies there, you get a decomposition that looks like this. So this is sort of the first ingredient. So what about the second ingredient? So I need just a little bit of notation here. So remember I had x mapping to y. I called this f. I called the inclusion here I. And let me call the inclusion of z as the ramification divisor j. So, OK, so here's some notation. For every k which is in z mod n, we can consider the following two functors. So the first one I'll call fk pullback. So this is a functor which maps. It's a composition of two things. So what are these two functors? The first one here is given by tensoring with the character chi k. I should say here the action is the trivial action. Okay, and then the second functor is just given by f pullback. And since f is equivariant with the original action on x and the trivial action on y, you get a pullback functor like this. So this is what I call fk pullback. Similarly, we can look at jk push forward and the composition of the two analogous functors. So here's j push forward. Here the action is, again, the trivial action. And here is just given by tensoring with chi k. So we have these two functors from d of y into this equivariant category and from d of z. And so here's the theorem. The theorem says that, so these two functors, fk pullback and jk push forward, these are both fully faithful. So they really give copies of d of y and d of z inside of this equivariant category. And moreover, there's a decomposition that looks like this. So there's one copy of y, and then there are n minus 1 copies of dz. Okay, so this is the theorem, and so this is some kind of folklore result. At least one reference I could find is that, so Ishii and Ueda proved a decomposition for any root stack, and X mod UN is an example of a root stack. So you can deduce from what they proved this decomposition, or you can just prove it directly. But anyway, there's a decomposition of this equivariant category that looks like this. And so let's analyze this in terms of the number of B's and the number of AZs that you have. So if you look at this thing, what do we have? So we have n minus 1 of these AZs. So what I'm doing is I'm plugging in the decomposition for D of Z and the decomposition for D of Y. So for each Z, I get an AZ. And then how many copies of B do I have? Well, remember, Y had M copies of B. So this is M plus n minus 1 times M minus ND B's. Okay, so now if you look at these two numbers, this number is the same as this number here, if you unwind it in your head. So what I'm saying is we have these two decompositions. They both have this category we're interested in, and then there's n minus 1 copies of AZ, and they have the same number of copies of this category B. However, these B's are embedded in different ways, right? On this side, they're given by pulling back some copies from Y and tensoring them with some characters, maybe. On this side, they're all pushed forward from this category Z, and then there are M of them coming from Y. So they don't really match up. So the last step in the proof of the theorem sort of, I mean, this is sort of where all the work is, and I'm going to suppress it, but you have to apply mutation functors. So maybe I'll just say that in general, if you're given a semi-orthogonal decomposition, there's a way to rearrange the components of the decomposition via something called mutation functors. And what we do is we apply a bunch of the, you have to do a somewhat complicated sequence of mutations on this decomposition here. And in the end, what you end up getting is a decomposition that looks like this. So there are n minus 1 copies of this category AZ. And then there are a bunch of B's. And they're exactly the same B's as in step 1 over there. So what I mean by the same B's is that they're embedded in precisely the same way. So once you've proved this, then you've proved the theorem. And the reason is that this decomposition here, it characterizes this category as the orthogonal to all of these B's. And so it has to coincide with this semi-orthogonal sequence. So once you have something like this, you get the statement of at least the first part of the theorem. And I'm not telling you how to actually do these mutations, but maybe I can just tell you what the formula for these functors looks like. So here this functor phi k is given by the following expression. So maybe I'll write it down and then I'll say something about it. Okay, so I mean, the main expression, so this functor is somewhat complicated, but the main term is this one right here. And so this is an example of one of these mutation functors, which I think I won't define for you, but if you've seen them before, that's good. Or otherwise, it's some kind of functor associated to this sequence of categories. And so this is an expression for these functors phi k. And for instance, what it shows is that if you want, notice that all of these functors have the same first part, and then the last part is just tensoring with this chi k. So in particular, this phi k of AZ is really just phi naught of AZ tensored with chi-k. So you can also write the decomposition in this way, which maybe looks a little bit nicer. OK, so this is how you prove. This is an idea of how you prove the first part of this theorem. And maybe in the last minute, I can just say something about this n equals 2 case. So so in this n equals 2 case, what do we have? So in fact, in general, in the case when n is just arbitrary, you always have an action on this category by z mod n, where here I'm thinking of z mod n as the characters of mu n. And it's just a general fact that holds in this case that if you look at the equivariant category of this equivariant category with respect to this action, that's actually just equivalent to the original category AX. So this again is, I think, sort of a folklore result, but at least one proof was given by Elegant. So it's the same Elegant from over here. And so once you know this, I mean, you immediately get the second part of the statement here. But the interesting thing is that we're able to identify explicitly the action of this z mod 2 on AZ. I mean, if I just told you this, how would you define this action? You would say you go by phi naught to here, you tensor with chi, and then you come back. But in fact, so we introduce a certain class of functors, which we call rotation functors. And I mean, maybe it's not so, maybe I won't write down the formula because I don't have a lot of time left. But I'll say that you can write an explicit functor down which gives this action of z mod 2 on this category. And so the way that you can think of this is that AX is completely determined by this category AZ with this extra data of a functor on it. And I think that's kind of interesting because it turns out that these categories AX and AZ, they behave very closely, at least in some cases, to the Hodge structure of the varieties you're considering. And in general, if you're just working with Hodge structures, there's not usually a way to recover directly the Hodge structure of the cyclic cover in terms of the Hodge structure of the thing you're branching over. But what the theorem says is that at the level of derived categories, you can do this. OK, so I think that's all. Thanks.